Hello, this is Anushya, the partner marketer at Econ Systems, your host for today. We are excited to welcome you to our joint webinar on Maximize the Power of FPGAs in Embedded Vision Systems. Today's session features experts from Lattice Semiconductor and Econ Systems. There will be a live Q&A session at the end, so please submit your questions in the Q&A box at any time. Let's go ahead and meet our speakers. First, we have Gambus Galilian, the Director of Strategic Initiatives and Ecosystem Partnerships at Lattice Semiconductor. Gambus is a seasoned professional with 27 plus years of experience in the semiconductor industry, spanning roles from FPGA and IC design engineering to marketing and business development. One of the main focus areas throughout his career has been the development of video and imaging related semiconductor solutions. Next, we have Anand Raj, the Senior Architect, FPGA Development at Econ Systems with over 18 years of experience in embedded vision. His extensive expertise spans hardware, FPGA, and mechanical design, making him a versatile and invaluable asset in the field. Anand Raj has played a pivotal role in developing and implementing high-speed interfacing solutions crucial to the success of embedded vision products. Over to you, Gambus.
Thanks, Anushya. Hello, everyone. And before I start, I would like to thank Econ Systems for organizing this joint webinar and inviting Lattice to join him in discussing this exciting topic. On this slide, you can see an overview of my section. After a brief overview on Lattice, we will discuss our products and solutions targeting embedded vision and edge AI applications. Okay, quick overview on Lattice before I dive deeper into the Lattice products and solutions targeting embedded vision and edge AI. Lattice is all about FPGAs. You can find Lattice FPGAs in all kinds of market segments and applications, even in some applications where you do not expect to see or find an FPGA. For example, you can find Lattice FPGAs in smartphones and computer notebooks, shipping in high volumes and even in aerospace applications. And you'll find Lattice FPGAs running cool in applications where competing FPGAs cannot play or would require a big heatsink. We have been in business for over 40 years. We're the world's largest FPGA supplier in terms of volume. We ship every year more FPGAs than all other FPGA vendors combined. We have a very large customer base, something around 1,000 customers worldwide, and we continue to expand in new markets and applications. We have a strong global presence with engineering sites and sales offices in all key markets. Now let's have a closer look at our FPGA product portfolio. The two most recent FPGA platform releases are the Nexus and Avant FPGA platforms, each consisting of multiple FPGA families. Nexus FPGAs are considered small FPGAs with transceiver options up to 10 gig and FPGA densities up to 100 kilologic cells. Avant FPGAs have transceiver options up to 25G and density options up to 500 kilologic cells. What distinguishes our Nexus and Avant FPGAs from competing devices in a similar class is that our FPGAs are based on low power and smaller process technologies. They consume much less power and we offer much smaller package options. In addition, we offer newer interface technologies compared to the competing devices in the same class. In this slide, you can see a categorized view of our FPGA product families. On the general purpose, you can see Avant being the most recent, targeting the mid-range, followed by lower density FPGAs such as Certus, Certus Pro, which are based on Nexus platform, and then also the ECP FPGA families, for example, ECP5 and ECP3. The bottom row highlights the more targeted FPGAs, such as the Crosslink FPGA family, targeting video and vision applications. The devices in the Crosslink family have hardened MIPI DeFi interfaces, which can support up to 2.5 gig per lane. Other than the FPGAs, we offer solution stacks targeting specific market segments and applications. We have released multiple stacks with Drive targeting the automotive market segment, ORAN targeting the comms market, Automate targeting industrial automation, Sentry targeting security and server market, Envision is targeting embedded vision, and Sense AI is targeting edge AI applications. We'll have a closer look at the last two solution stacks, Envision and Sense AI. Sense AI is our solution stack targeting edge AI applications. Each of the solution stacks is supporting a range of FPGA families. You can see the families listed at the bottom of the stack. As you can see, ICE40 Ultra Plus, Crosslink NX, Certus Pro NX, ECP5, and Avant FPGA families are supported. From bottom to top, you can see the green lane labeled hardware platforms, listing some of the evaluation boards and kits supporting our edge AI solutions. Next are the IP cores, which consist of different CNN accelerators. Next are the software tools containing our Radiant and Diamond FPGA design tool chains, and Lattice Propel for embedded, Glance for advanced attention sensing, and various machine learning frameworks such as TensorFlow, TensorFlow Lite, Keras, and Caffe are supported. This slide gives you an overview of throughput versus performance. You can see what applications are supported across which FPGA families. Starting with ICE40 Ultra Plus, one of our smaller FPGAs, pictured on the left-hand side next to the pencil. It's 2.15 by 2.55 millimeter, less than 55 square millimeters. Yes, it's that small, and it can run AI, and it consumes only 1 to 20 milliwatts. And you can run various AI applications on it, such as object detection or key phrase detection. Obviously, as you go up in FPGA density and performance, you can run much more complex algorithms and even run multiple engines in parallel. When I showed the Sense AI solution stack slide, I highlighted that we offer different flavors of CNN IP cores. These CNN IP cores include convolution, fully connected layers, nonlinear functions, max pooling, and other blocks. These IP cores are optimized and differ in size and performance on chip memory utilization and allowing you to tailor your design to your application requirements and potentially use the remaining FPGA resources for other implementations, such as MIPI signal aggregation or implementing a high-quality ISP pipeline along your CNN accelerator. We are discussing the Sense AI solution stack, and in terms of software tools, for training, you can train your models using TensorFlow, TensorFlow Lite, Keras, or Caffe machine learning frameworks, and then compile the trained model and generate weights and instructions. And depending on which target FPGA device you select, you can use either Radiant or Diamond tool and generate your bit stream and program the FPGA with it. In this slide, you can see an example on an FPGA implementation for computer vision applications. On the left-hand side of the block diagram, you have your MIPI input interfacing and image capture blocks, followed by ISP preprocessing for AI, and then the CNN engine, which is listed here as AI accelerator, and then also your CPU and memory subsystems. Here you can see some example use cases that have been implemented on different Lattice FPGAs. For example, ICE40, ECP5, Crosslink NX, and Certus Pro NX FPGAs. Example use cases here range from object detection to object classification at different performance levels, utilizing different CNN engines implemented on different Lattice FPGAs. All right, we just completed the Sense AI stack overview, and we'll now discuss the Envision stack. The Envision stack supports a broad range of FPGA families and includes, same as all our other solution stacks, hardware platforms, IP cores, FPGA, and embedded design tools. It also includes reference designs, and the stack is also supported by a wide range of ecosystem partners servicing different target application areas. We will now discuss each swim lane in more detail. This is an overview of the IP cores supported by the stack. It includes display processing, image signal processing, bridging, and connectivity IP. Other than IP cores, we also provide demos and reference designs, which can be used as examples for starting your FPGA design. On the software tool side, same as discussed before, we also provide a framework for ISP development and configuration. Our stack components are also supported by our ecosystem partners. As an ISP example utilizing Lattice FPGAs and software tools, I would like to highlight Econ Systems Tint-E ISP. I have copy-pasted these images from Econ Systems website. I have added the link at the bottom of the page. You can check out the ISP implementation on their website in more detail. It's pretty cool. You can click on each individual ISP block and see the before-after impact on the processed image. To show you some examples, I clicked on the debayer block and white balance block and copied the associated before-after pictures as seen here. This ISP has been implemented on multiple Lattice FPGA families, including a 4K ISP version. The ISP is available for evaluation and licensing from Econ Systems directly. Econ Systems also provides custom design services around Lattice FPGAs and their Tint-E ISP. Other than standard dev kits for each FPGA family, we also provide FPGA boards specifically targeted for embedded vision applications. Here you can see some boards and kits examples based on Lattice FPGAs developed by Econ Systems. On the left is an example of a 4K RGB IR camera with USB 3.2 output. On the right is a 4K monochrome version with USB 3.1 output. And in the middle is a 3D time-of-flight USB camera for depth sensing. These are all available from Econ Systems and are based on Lattice FPGAs. Our ecosystem partners and their IP cores, reference designs, and design services are a major component of our success. And we have partnered with Econ Systems for developing customized embedded vision solutions based on Lattice FPGAs. This is my last slide, and before I hand over to Anandraj, I would like to close my section with a recent and very exciting success story. As you may know, Econ Systems is an elite NVIDIA partner. Econ is also a premium Lattice partner. So NVIDIA and Lattice have teamed up with Econ Systems in supporting and providing solutions around NVIDIA's Holoscan sensor bridge reference design, which is based on Lattice FPGAs. The Lattice FPGA-based reference design can ingest multiple image sensors or other type of sensors and stream the data via 10G Ethernet pipes to an IGX or AGX platform for AI processing. This reference design is supported by NVIDIA's Holoscan software development kit. Holoscan is a full-stack AI platform for real-time processing of streaming data at the edge or in the cloud. Econ Systems is supporting the Holoscan platform with image sensor solutions, ISP, and custom design services. Thanks. And back to you, Anandraj.
Thanks, Canvas. Hello, everyone. Let us see the significance of FPGA in embedded vision product, and we can see how usage of FPGAs can maximize the embedded vision product. Typical architecture of an embedded vision product. This is a typical architecture of an embedded vision product. The image sensors and the displays are connected to an application processor. The image sensor will send the data to processor. The processor will receive the image data. The received image is processed at the processor and sent to display for user interaction. There are three crucial parts. First is connectivity, which is the interface connection between the sensor to processor and processor to display. The next one is high performance, which is the processing capability of a processor. The next one is the low power, which is power consumption of the processor. The most common challenges in embedded vision products are limitation in number of ports. That is, processor will have 2 MIPI camera interface, but we may need to connect 4 MIPI cameras. Processor doesn't have the required interface ports. Camera is sending a data in SLVS EC interface, but the host processor is having only MIPI. The latency is more in CPU, can be processed at the edge, need high processing power with low power dissipation to run an AA/ML model. To complete, design should be easy, portable, and flexible considering the future. The architecture must adopt the latest technology sensor without changing the host processor. Nowadays, major applications like surround view, collision detection, sports broadcasting, etc. demands for multiple camera solution, but processor has a limited number of interface ports. This block diagram is one such example where we have 4 MIPI cameras, but the processor has only one GMSL port. How do we interface this? This challenge can be addressed by using an FPGA in between MIPI camera and application processor. In this block diagram, FPGA will act as an aggregator. The FPGA will receive the image data from 4 MIPI cameras, aggregate, send via single MIPI output. Then it is converted to GMSL and sent to host processor. Since FPGA offers a wide range of high-speed interfaces like MIPI, PCIe, Ethernet, sub-LVDS, and SLVS EC, aggregation is possible in all the high-speed interfaces. The next challenge is unavailability of the required interface ports, but I can't change my host processor for this reason. In this block diagram, image sensor can send data via either MIPI or SLVS EC interface, but the processor can accept data on PCIe or USB interface. Another challenge in this block diagram is to match the bandwidth between the two different type of interfaces. This challenge can be addressed by using an FPGA as a bridge in between the sensor and processor. We can also interface DDR to FPGA to solve the bandwidth conflict between the sensor and processor. In this block diagram, FPGA is acting as a bridge between an SLVS EC and PCIe interface. FPGAs have production-ready full-stack options for many interfaces like Ethernet, PCIe, USB, etc. This will enable us to launch the product in short span of time. For an embedded vision product, we can consider using a Lattice mVision and Sense AI stack to reduce the development time. We can also use FPGAs for bridging display interfaces. Few displays will have custom interface or custom resolution or custom timing requirement. The host processor cannot fulfill this requirement. We must have to do bit banking in the processor to support this type of displays. In this case, most of the CPU load will be consumed for display. We can use FPGAs to bridge the gap and leverage the CPU for algorithm processing. Few applications in automotive, medical requires multiple display solution, but host processor will have limited display ports, or it may not have supported same image content in different display port with different resolution. FPGAs can be used for multiple display solutions. FPGAs have the flexibility to support the multiple display and multiple resolution, where one display can be configured for 4K at 30 frames per second and the other one can be configured for Full HD at 30 frames per second. As we had seen multiple options for connectivity, the next thing on the embedded vision product is executing an algorithm. If we want to run an image signal processing algorithm or application specific algorithm to add smartness on the product, we must consider three key parameters. High processing power, this is needed to execute a complex algorithm. Low latency, this is needed for faster execution of algorithm. Low power consumption to reduce the thermal dissipation. When we execute an algorithm, it will be divided into multiple tasks. The CPU will execute each task one by one in a sequential way. Since FPGA's internal architecture comprises of abundant logical elements and DSP slices with parallel connectivity, FPGA can execute all the tasks in parallel. Since FPGA is executing tasks in parallel, we can reduce the processing time and latency. When we want to execute an AA/ML algorithm, in most of the cases, the building blocks is convolution. The block diagram shows us an example of 3x3 kernel convolution. To execute a 3x3 convolution, CPU will take approximately 17 clock cycles, but In case of FPGA, it can be executed in 2 to 3 clock cycles. In CPU, the ALU will fetch, decode, and execute each instruction sequentially, but FPGAs will execute complete operations parallelly. Since most of the edge devices are battery operated, they are sensitive to power consumption. FPGAs will provide more operations per watt compared to GPU. Some of the lattice FPGA series will consume less than 70 microamps of current in standby mode, which can help us in two ways. One is operation time of a product will be more for a single charge cycle. The next one is we can reduce the thermal dissipation and avoid using heat sinks. In an embedded vision product, ISP is the basic block needed to get an quality images. It can be implemented in two different ways. As shown in the block diagram, one on the left uses an inbuilt ISP from the processor. The other one is the right, which is having an FPGA ISP outside the processor. The bottleneck in the left side implementation is if an application processor requires 14-bit depth data for algorithm processing, the ISP inside the processor is supporting maximum of 12-bit depth data. If we want to support 14-bit depth data, we need to change the host processor, which requires huge time and effort. In case of FPGA ISP, we can reprogram dynamically to support either 12-bit or 14-bit depth data. The FPGA ISP architecture is more flexible with high processing power and low power consumption. We can see a demo of Econ Systems C3CAM 50 CUG embedded vision camera, which uses lattice crosslink FPGA. In C3CAM 50 CUG, FPGAs have been used for interface bridging and also to run an Econ System proprietary TINTI ISP. In this demo, we can see the controls of TINTI ISP for changing brightness, contrast, exposure time, individual gains of RGB pixels, etc., and the image quality of an indoor and outdoor environment. So this is a 50 CUG camera streaming in indoor application where you can see we can able to change the controls. So now the brightness control is changed. Now we can see the contrast is getting changed. So now the black level is adjusted. So now the gamma is getting corrected, changed. So these are the images in indoor applications. So we can see the exposure time is changed. So this is an individual RGB gain and a different color temperature is getting changed here. So this is an image of an outdoor application. Yeah, thanks.
Thank you, Anand and Gambus, for your invaluable insights. Let's move on to the Q&A segment. You can now ask your questions. Here we got one. Why use FPGA for Edge AI? There are many other choices in the market.
Yeah, I'll take this question. So yeah, the question was why use FPGAs for Edge AI, and there's other choices in the market, right? So I would say one of the key advantage is lower power consumption, right? For example, I showed you some data on the slides, right? We can do human presence detection at 1 milliwatt, right? Another one is form factor, right? You also saw some examples of package sizes, for example, device sizes in the slides. So in general, FPGAs offer a parallel compute architecture. So you can have an optimized pipeline design. Other aspects are, for example, the hardware configurability or programmability of the device over its entire product life cycle. So you can continue tuning your design or reload the FPGA with a new design. You can change models. You can use new models with higher accuracy as they become available. So FPGAs can also support multiple use cases and run these use cases at the same time. You can add custom functions, for example, ISP, right? We talked about that. You can add a high quality ISP to your device if that's what you need for your application. BOM reduction is another one, right? You could absorb other BOM components inside your FPGA. So yeah, I think FPGAs in general are a great choice for edge AI applications.
Got it, Canvas. Another question. Can we sync multiple cameras with FPGAs?
Yes, definitely it is possible. We can able to synchronize multiple cameras using an FPGA by connecting the trigger signal of a sensor from the FPGA.
Thank you, Anand. Another question. Are there any specific optimizations to Nexus and Avant for AI processing?
Yes, absolutely. So, first of all, from selecting the right process technologies, right, to product features. So these products have been designed with embedded vision and edge AI applications in mind. So distributed memory, fracturable DSP engines, flexible I/O for supporting many types of sensors and host interfaces. So those are some of the examples.
All right, Canvas. Another question for Lattice. Do you support other types of image sensor interfaces or only MIPI?
Yes, we do. So that's the beauty of FPGAs, right? We can support all kinds of LVDS, sub-LVDS types of interfaces. We also support Sony SLVS EC interface, for example. So that's another great use case, right? Converting SLVS EC to MIPI, PCI Express, Ethernet, right? So cross convert, right? Sensor formats to other type of interfaces. So absolutely, we support more than MIPI, CSI2, DSI. Yeah.
Okay, Canvas. We got another question. With an Ethernet UDP camera, how much bandwidth can we achieve?
Yes. Um, from an Ethernet camera, we can able to achieve a bandwidth. Basically, it depends on two parameters. One is the host, then next is an application which is getting streamed for a camera. So bandwidth depends on these two cases. In practical, when we connect when we connect and between an FPGAs, we can able to achieve 95% of an bandwidth. When we connect an camera to an host platform like x86 or we have achieved almost 60 to 70 percentage of the bandwidth.
Noted, Anand. Another question. Do I need to understand FPGAs to design a system?
Good question. So our goal is to enable non-FPGA experts to also be able to utilize our AI solutions. So we provide different tools, right, to help folks without FPGA experience. For example, System Builder. We provide complete reference designs and development boards and kits and modules. We provide production-ready AI models, for example, for HMI, including presence, attention, sensing, ID, and gesture. We also have a partner network which can also support your AI development process.
Got it, Canvas. Another question. Are the smaller cameras that have the advanced Tinty logic to fit enclosures more easily, than the rather huge 50 CUG?
Yes, definitely we have a smaller cameras, smaller than 50 CEG. But in terms of size, definitely, in terms of logics, definitely we can able to comprise we can able to reduce the FPGA logics by removing few blocks in FPGA models to reduce the entire logic elements as per the application. And in terms of physical size, definitely we do have a smaller miniature camera lesser than 50 cg size.
All right, Anand. I think there's another question for Econ. Is it possible to get the custom stats data from FPGA ISP?
Yes, definitely it is possible. So by default, the Tinty ISP will comes with a few statistical data. If a customer or an application demands for an custom statistical data for an application or edge A processing, definitely it is possible to support.
All right, Anand. Here we got another question. Can we aggregate multiple cameras with different interfaces, MIPI or sub LVDS to USB?
Yes, we can definitely we can aggregate multiple cameras, whether it is some different interface also, either it can be a MIPI, sub LVDS or SLVS. We can able to aggregate between different type of interfaces.
One last question. Why choose Lattice FPGAs instead of other FPGAs?
Uh, that's a good question. So that's a very generic question, right? So in general, um, Lattice devices consume. I talked about the process technologies and some of the benefits over competing devices in the same class, right? So in general, Lattice devices consume much less power. So you don't need to use a big ass heat sinks with Lattice FPGAs, right? So oftentimes you see these big heat sinks on competing FPGAs, and the Lattice devices in a similar class, they run cold, so without a heat sink. We also provide much smaller form factor, smaller packages, right? And in terms of what we talked about here, embedded vision and edge AI, we offer small FPGAs with hardened MIPI D-PHY, for example, right? So ideal for camera and imaging applications. And we offer FPGA devices generally architected to support embedded vision and edge AI implementations, right? So they have been optimized. So from process technology to design optimization, right? In terms of DSP, memory subsystem, I/O, etc., right? Supporting edge AI applications.
Got it, Gambus. So we have answered most of the questions and we'll be sending the remaining answers via email. Thank you all for joining us today. We hope you found the session valuable. If you have more questions or need more info, write to us at camerasolutions@e-consystems.com or please visit us at www.e-consystems.com. If you're unable to attend the full webinar, rest assured that we'll be sending the complete webinar recording to all the registrants. Stay tuned to our social media for updates on more webinars from Econ Systems. Thank you and have a great day.